Just to review this, laws of indices, we've assumed that the base, remember this is the base, is the same, and if the base is the same and I'm multiplying two numbers together, I add the powers. If the base is the same and I divide, I subtract the powers. We can expand these two basic laws of indices to arrive at four more, which we looked at last week. So those are the laws of indices, and when we come on to Unit 1, which is assignment 1, where we do a lot more algebra, then we'll be using these laws of indices a bit more extensively. And certainly when we come to do differentiation in calculus, you'll need to use those laws of indices in there. So they're going to become more and more important as time goes on. So you'll get to know them. We could extend that a bit further and arrive at these laws of logarithms that come from this. Okay. So laws of logarithms. Remember we were saying last time that a logarithm is a power. It's a power of 10. If there's no base mentioned, it's a power, and usually of 10. Certainly if you look at the logarithm on your calculator, that log button means power of 10. So if I find the log of something, I'm finding the power to which 10 is raised to give that number. So the log of 3, if we just look at that as an example, is 0.477, one more, right, okay, 4771. That's telling me that 10 to the power, so therefore 10 to the power 0.4771 should be, and it won't be exactly because of rounding issues, 3. And that's what we were saying last week. Logarithms turn numbers into a power. I've turned the number 3 into a power of 10. And that means I can use the laws of indices. And we can turn multiplication into addition. Because when I multiply, I add the powers. Division becomes subtraction. Because when I multiply two numbers, I subtract the powers. And the one that we're going to use this week, bit more, is this final one, which I said at the time was going to be an important one. So those are the laws of logarithms that we wrote down, and we're going to be using those today. So today we're going to look at those two things. Solving indicial equations. We'll look at what an indicial equation is and look at some examples. And the use of these logarithms in power functions. I've included this bit because it follows on directly from the work on indicial equations and these laws of logarithms here that we've quoted. So as well as using them to solve indicial equations, we use them in these power functions. Really, the power functions work that you're going to do on this comes into Unit 28, which you're doing in Semester 2. But because this falls naturally in this place, I'm going to do it now. So what we're going to do is some of the work towards Unit 28 at this point. So that means that when we get to it in Unit 28 next semester, we won't have to worry about it. So that's the aim for today. First thing then is to try and use this idea to solve indicial equations. So let's look at an example. 2tx equals 3.6. It's called an indicial equation, this, because it involves the power. In this particular example, we've got to find the power x. So if the power is part of the problem, in a way, it's an indicial equation. So in this case, we've got to find the power. And invariably, if you've got an indicial equation or the power is involved, we use logarithms. So to solve an equation like this, I find the logarithm of both sides. If you think about what we've been doing with equations so far, whatever you do to one side of the equation, so long as you do the same thing to the other side, it's still a balanced equation. So if I add something to both sides of the equation, that's fine. If I subtract something from one side of an equation, so long as I subtract it from the other side as well, it's still balanced. I can multiply, I can divide, I could square both sides, and it's still balanced. a square root one side so long as a square root the other, and so on. So I can just as easily find the logarithm of both sides, and so that's what we do. We find the logarithm of 2 to the x equals the logarithm of 3.6. We do this because now I've turned this number, 2 to the x, into a power by making it into a logarithm. So that means I can use the laws of logarithms. And look at this last one. The logarithm of a to the power n, the n, comes down and turns into a multiply. So in other words, we can use that here, and we can say this means that, therefore, x times the logarithm of 2 equals the logarithm of 3.6. And we brought the power down and turn it into a multiply. And that's the point of it. Now it's like a straight equation. X times a number. Log 2 is just a number. We could work out what that was just by hitting log 2 on the calculator. It's just a number. So x is multiplied by log 2. So to get x on its own, divide by log 2. And x equals log 3.6 divided by log 2. And now we get the calculator out, work it out, and that tells us x. So answer x 1.848. Try and hold some significance because remember these are powers. How would we check that this was right? Go back to the question. 2 to the x equals 3.6. So what can we do now to check this is right? Right, so to check, and we always look for ways to check these things, 2 to the 1.848 should within a little bit equal 3. 3.6. So that's quite a long way out then. Oh yeah, of course you did. Thank you. I forgot that. That's right. So pretty close. Yeah. So x to the 3.2 equals 12. This time x is not in the power, but the power is certainly an issue. We could do with getting rid of that 3.2 in the power and turning that into a multiply. So same first step. Find the logarithm of both sides. Logarithm of x to the power 3.2 equals the logarithm of 12, which means that we can use the third law of logarithms and turn that power into a multiply. 3.2 times the logarithm of x equals the logarithm of 12. So far so good. We've now got an equation. We've got rid of the power. Log 2. Log 12 is a number, and so is the log of x. So this is a number, the log of x. I can't sort of multiply or divide by log to get rid of the log to get x, because that's part of this number. So we're going to have to think about that again in a minute. But what we can get rid of is a 3.2. So if I divide both sides by 3.2, I get the log of x equals the log of 12 divided by 3.2, and I can certainly work out what that is on a calculator. So I can say the log of x equals, so the log of x is 0.3372. Now we just have to remind ourselves what logarithms are, and if you remember at the beginning of today I wrote down an example of the logarithm. If the log of 3 is 0.4771, then 10 to the power 0.4771 gives me back my 3. So what I have to do here is work out what, to get x, that's going to be 10 to the power 0.3372. So if you're told what the log, if we want to find x and we know the log of x, then it's 10 to the power. And if you look at the calculator, you can see that's actually above the logarithm button. So in other words, it's the opposite of logarithm. So x equals shift hit the log, shift log button, you'll get 10 to the power, and that gives you so about 2.173 to 4 significant figures. Again, how would we check? Work out what 2.1743 to the power 3.2 is. So as a check, 2.173 to the power 3.2 should give near enough 12. So not bad, okay? So logarithms are very useful for bringing powers down and turning into multiplications to allow us to solve equations. Let's look at another example. Okay, let's look at this. I want to try and solve, by using logarithms, this indicial equation. So I'm going to take the logarithm of both sides, which means that those powers can come down and turn into multiplications. And then we've got an equation to solve. But just before we do that, let's look at this one as a little aside. Something we may have looked at before, examples of before, okay? I've got x's on both sides of the equation, so what sort of things am I going to do to try and solve this equation? What am I after doing? Get like terms together. Yep, so I'm going to get all the x's on one side of the equation. Right, Michael? Yep. So if we look at this, if I subtract 4x from both sides of this equation, look, that means this 4x is gone because I've subtracted it. But if I subtract 4x from this side, I'm going to have 2x minus 4x is minus 2x. So minus 2x is not that convenient, making the x is negative. So a better way to go around is to subtract 2x from this side to get rid of it, and 2x from this side. So subtract the smaller number of x's from both sides, and I end up with 3 equals 2x minus 2. I've subtracted 2x from both sides. You see how that works? Yeah. And now what I do is I get the numbers on the same side. I've got 2x minus 2. Let's add the 2 to both sides to get rid of this. So add 2 to both sides. I've got 5 equals 2x. And so you can see at each step I'm making it much, much easier. And now all I've got to do to find x is divide both sides by 2. So finally x equals 5 divided by 2. So I don't know whether you thought that looked like an awkward equation at the start. Maybe you didn't, but that's what you do. You get all the x's on one side, as Michael says, get like terms together. And then once you've done that, so I've got the x's on the right and the numbers on the left, I then can solve it. Okay, and we're going to use that idea to solve this. So let's take the logarithm of both sides of this indicial equation, and then we can, in one step, write the x plus 1 in front, because this x plus 1 now becomes multiply if I take logarithms, and so is this. So I can actually go straight to writing this. X plus 1 times the logarithm of 2 equals 2x minus 1 times the logarithm of 3. At this point, it's worth considering our options and try to make life easy for ourselves in solving this. I could expand out these brackets. X times log 2 to give log 2 times x. Log 2 times 1 equals 2x times log 3 minus 1 times log 3. But the trouble is, log 2 and log 3, we know, because we've done it already, if you work out what they are, they're decimal numbers to many significant figures, and we have to round them. So we're making the calculation a little bit awkward for ourselves if we expand out the brackets. The best thing to do is to divide both sides either by log 3 to get rid of log 3 on this side and leave divide by log 3 over here, or the other way around. The question is, which is the most convenient way to do it? If I divide both sides by log 2, I've got log 3 over log 2 times this bracket. If I divide both sides by log 3, I've got log 2 over log 3. times this bracket, and that's the easier one to expand. So with just a little bit of thought, I would decide to divide both sides by log 3, because this is the easier bracket to expand out. So dividing both sides by log 3 gives this. So now calculate log 2 over log 3 to say 4 or 5 significant figures, because these are powers, so hold on to the accuracy. So x plus 1 times 0.6309 equals 2x minus 1. Now we multiply out the brackets, and you can see that that's made life very easy for us now, because it's just 0.6309x plus 0.6309 equals 2x minus 1. So we expand out the brackets and we get this. Okay, now we think back to the aside we just did, look, and that's very like this aside. We've got x's both sides of the equation and numbers both sides of the equation. So as before, we try and get all the x's on one side and the numbers on the other. Remember the criteria we used? We subtracted the smallest number of x's, so we left ourselves with a positive value for x. So if we go to here, I've got 0.6309x this side and 2x this side. So subtract 0.6309x from both sides, which will leave me 0.6309 on the left equals, what's 2 take away 0.6309? So it equals 1.3691 lots of x minus 1. And now we get rid of the number on the right hand side by adding 1 to both sides. So 1.6309 equals 1.3691 lots of x. So we just now divide both sides by 1.3691. 1.6309 divided by x equals 1.191 to 4 significant figures. How would we check in this original formula? Yeah, plus 1, and work out what that is, and then work out the right hand side, putting in the substitution value for x, and you should get the same answer both ways. So that's how you check. So check by calculating both sides of the equation. And see if you get the same answer. Original equation. Okay, so turn to page 103 in the textbooks, exercise 54, and have a go at some of those questions, please. I'm going to give you about 10 minutes, quarter of an hour or so, to try out this question. Note the last question in the exercise is a practical example of the use of these logarithms to find decibel gain in a power amplifier. So try as many as you can in this exercise.